Okay, so let's continue. Next, I want to explain the quantization. But before I come to this point, let me actually summarize a little bit what we have achieved. And this is actually the starting point toward quantization. So what's really happening is the following, like in summary. So originally, we have a space, S plus. And we have actually a DGLA describing the moduli space. Then we see, like, if you're using this period map to this kind of Lagrangian, and then you project down to S plus again, and you basically discovered a new homological vector field, delta. This is a Q plus bracket. You can summarize this one as saying that this defines an L infinity structure. So you have this L1, and this described to you like L2 and L3, all this higher stuff, because this is like an infinite sum. This is all the higher stuff. And you can write down the corresponding Maury-Cartan equation like Q mu plus summation Lk, 1 over k factorial, Lk, mu to the k equals 0. Now this is a highly nonlinear equation, but the good point of this one is like this part is basically the critical point of this action functional. So it's a DG and critical point. And this looks much more complicated, but this is actually equivalent to the original problem because the composition is a diffeomorphism. So this is pi plus composed with period map. So this nonlinear map, which map, let's say, a mu to t 1 minus exponential, and then project down to the non-negative part. This nonlinear transformation really maps diffeomorphically a solution here to a solution here. So we use a very complicated way arising from period map to change our original geometric problem into a more complicated expression. But the good point here is like this one has an action functional. No. So my classical action or classical interaction. As I mentioned, like the original equation, there's no way to write this one as a critical point. So this is really the starting point of the story, which allows us to understand quantization. Okay, so let me explain the idea of quantization. So the next one, I want to explain the so-called quantum BV master equation. Again, today I will explain the basic idea. So actually, start with the Toy model. So next time, I will tell you the more subtle thing about this infinite dimensional setting, the Toy model. Because this Toy model is our guiding principle. So again, we have this V, Q, omega, the same story as before. This is like DG symplectic. Okay, so the same story, and we have this Poisson kernel. Ricci curvature, no metric. That's the metric dependence that will, the dependence on metric will only enter when you do this gauge fixing story. No, so far. I need the club to write down the trace map. Yeah, the volume form.
The volume form.
Yeah. I haven't chosen any metric yet. So next time I will choose the metric to write down the renormalization stuff. So this is, if you work with infinite dimensional setting, you want to regularize it to a finite dimensional case, you need a metric. You can choose any metric. Okay. So at the level like doing this kind of a perturbative renormalization, if you allow counter terms, things like that, any metric would work. However, now we know if you choose the Kähler metric, a metric appears. The theory becomes degree finite. There's no counter terms.
I mean, if you choose Kähler metric or
Kähler metric.
Just Kähler metric.
Yeah. It's not clear yet whether you can remove this Kähler condition, but anyway. So now we have this the same story, like isotropic splitting, and Q preserve this object, but not preserve this V minus. And I wrote down this P, which is the metric tensor, as a failure of this object. And in this way, we obtained a DGBB algebra. Oh, yes. That's right, yeah. So this is a DGBB algebra. Okay, that's our starting point from last lecture. Now, from here, let's do quantization directly, because in the finite dimensional case, it's much simpler. Now, you think about this one as like a standard phase space. On the phase space, we know once we have a linear sympathetic structure, we know how to quantize. We basically obtain a Y algebra. And then we know the corresponding representation that's given by the Fock representation. So let's just write it down. But now we have to incorporate this Q. That's the Raphite symmetry. So we need to write down a DG version of that. And that's actually not the problem.
If you look at the symplectic form on the degree 1 part, is this symmetric or symmetric?
It paired degree 1 with degree minus 1. Yeah, so it's not in the same degree. So you can just put them together as a symmetrical or antisymmetrical way if you want. Yeah. Okay, now, so I assume people know quantum mechanics. So let's directly work it out. Yeah, this toy model is simple. So we defined the formal Y algebra so far we work in perturbation theory, so we work everything in terms of formal functions and so on. Non-formal things are extremely interesting. Hopefully I can tell you something later. So, but let's work on this perturbation theory.
So that question is for this because can you, because there you fix the background omega to do this. You're basically doing that on the tangent bundle over the moduli space. Can you do this over the moduli space and then have back connection?
Yeah, this is with respect to a reference point, first point, yeah.
But is that, so can you do something like Fedosov? This is just what you do at one point.
That's right. I mean, you can, and then you basically do what I'm going to say here, our family, and then Fedosov, for Y algebra it's rigid, so you can find a projective flat connection, and That's basically holomorphic anomaly equation. We move around.
So it's not flat.
Projective flat, yeah. So that projected flatness, that equation, literally, it is the holomorphic anomaly equation. Yeah.
So you mean that you're just doing this moving on.
Exactly. Yeah. It's much simpler if you work with like only like H3 on Calabi-Yau threefold. That's much smaller space. You can do this quantization, and that's what's essentially described by Witten in his paper on this background independence in string theory paper. Yeah.
But you can do this for
No. Even formal, yeah. You can work with like formal bundles and things like that. Yes. Yeah, that's actually where I started to play a little bit about this the Y algebra, the philosophy stuff. Basically, I wish to understand what's happening here. Yeah, but it goes to a different direction then. Okay, so this Y algebra in this case is defined to be like I'm gonna work with formal functions. And this tensors is like a formal tensors adjoint with like a H bar module relation. And what is this relation? So here H bar is a formal parameter, quantum parameter. And then the equivalence relation is the following. It's like take any two elements, A and B, lies in the redo. This is how you write down the wire quantization. So basically, commutator of A and B, which by definition is the A tensor B minus, because it's graded, B tensor A. This object has to be equivalent to H bar omega inverse pair with A and B. Let's say A tensor B. That's a standard Y algebra. Okay. So now you see, like somehow when you set H bar goes to 0, you obtain like a formal functions basically. So this object, if you mod out this H, it basically isomorphic to like formal functions on your space. The standard classical limit, let's say, and this might be, so this is formal functions. So that's the wire quantization. Now, let me write down the corresponding representation, the Fock space. So the Fock space is also easy to write down like this because it has a unique representation. So let's just figure it out. And we want to write everything to be a little bit be consistent with our choice here. So you think about this splitting as like specifying a creation annihilation operator. So that's roughly speaking what's happening. So let's denote like annihilator of this wave plus. Just the annihilator. Again, this is finite dimensional case. This is much easier. So in the infinite dimensional case, we have to do a little bit functional analysis, but I'm gonna do it later. So, so explicitly, this is given by all of the linear map, and you apply this one to V plus. This is one equals 0. Okay. Now, also like the differential Q, it acts on V and also acts on V plus. This implies dually, I'm gonna still write as a Q. Dually, this implies a differential on the dual vector space, and which preserves the annihilator. And that's sort of the dual description of this guy. So, roughly speaking, like this was like a subcomplex. So probably let me say right here. So this is a subcomplex. It's not only a subspace, but a subcomplex. Okay. Now, with this data, we can basically write it literally. This is also half of the data. We basically define the representation by declaring that this element here as an annihilation operator. So define the Fock space. The formal Fock space I'm gonna write this one as a fork of the data. So there's so many data, so I'm gonna just write one for this V plus. But this is bad notation. I agree about this, but anyway, that's the Y algebra quotient by the left ideal generated by this annihilator. So, in other words, so if you think about it, one as a vacuum state here, and this one says like, this is 0 means like, you think about this one trait. This object as annihilation operator. So this one applied to 1 is 0 in this Fock space.
Sorry, where is 1?
This the algebra.
Oh.
Yeah.
This is just function or mean quotient by V plus.
Yeah. It's you're right. It means a quotient space is just exact function. But now I want to incorporate the splitting. So because there's a differential here, I want to be compatible with the differential at some point. But so let me explain like step by step. This is actually a crucial point. So now observe. Q is compatible with omega. This implies a bunch of things. First, this relation is compatible with Q. So you see, like Q implies a differential on each dual space, and then implies by derivation on differential on the whole algebra. And then, because it's compatible with this omega, it descends to the quotient space by the equivalence relation. So I want to say this one is a well-defined chain complex, a cochain complex. So Q is really defined, really well defined on this quotient space of Y algebra. The number one. Second, because Q preserves the annihilation, so Q also preserves this ideal, left ideal. Also, this Y algebra annihilator is a subcomplex. Which implies that this induces a chain complex on the Fock space.
When you say chain complex or chain complex, it just means complex.
Oh yeah, okay. I really mean cochain complex because the degree increased by 1, so everything is just complex. Yes, yeah. Sometimes I confuse chain complex with cochain complex. For me, cochain complex increased degree by 1, and yeah, but it's just complex. Yes, you're right. Yeah. Okay, so this Fock space. Great. So we see like we really find something like the data is like, okay, well, we have this complex, we have this quotient representation, also complex, they're compatible. So we have all this data. Now, let us implement this splitting. So let's basically try to work this out explicitly. I mean, so using the splitting, so this splitting allows us to identify this one was cotangent of this plus V plus as I mentioned, and then you see like whenever we say Fock space, this is basically generated by half of the data, like creation operators. Now you can basically write these creation operators as functions on the V plus, because basically the other part is annihilators of management. So we can write, for example, denote. Let me say it this way. So this implies induce a natural embedding which is split the natural the other way. Okay, so basically extension by 0. Now, let's denote. I want to represent this Fock space in a rather explicit way. So let us write functions on V plus. I'm going to work with formal functions. So let me write O formal V plus to be this formal power series. This formal power series, formal function. And then with respect to this embedding, you see like this precisely describes the creation part of this Fock space. So roughly speaking, if you write this formal function, you introduce this formal variable. This embedding allows you to basically embed this object to wire algebra just by this extension. And this is also well defined because this is isotropic. So when you look at this invariance between objects here, it's going to be 0, so it's a symmetric function. So this is well defined because of isotropic embedding. And then this map to a quotient Fock space. And this is creation operator. So you see like this composition actually is isomorphism. Just basically the creation operators. So this is really all the creation operators. And this is how physicists write something like starting from a vacuum, you do some kind of a dagger things. This creation operators, something like that. This is the dagger things described by element in this from this formal function. Now, you see like the I just write here. So this is basically a diffeomorphism, like isomorphism. Now, what's really happening is the following: like, where's the data for the splitting, which somehow fails the differential. So you see, like, this one is a Chern complex. There's a Q here. Now, I also explained that there's a natural differential Q acting on the Fock space. So under this isomorphism, there's going to be an induced differential Q hat. Let me call it one Q hat acting on here. That's the induced differential by this isomorphism. You want to make a guess, like what this one look like? So let me erase this part. So let Q hat be the induced differential on this space. So in terms of this community diagram, it's like, let me just be slow. So isomorphism. So this is a unique one, making this diagram to mutes. So what kind of differential we can write down on this object? So first of all, you see like the Q, this O, the function on V plus has an induced differential from the differential Q on V plus. So I'm gonna erase this part. First of all, the differential Q on V plus induced by duality a differential on the dual space and the corresponding differential on functions. So I'm gonna still denote it by Q. So there's actually a natural induced differential. However, this one is not the same as this operator. Basically, because the splitting is not compatible with the differential. If the splitting is compatible, literally, it's going to be the same as the Q. And let me just write down the proposition. And this Q hat literally equals Q plus the quantum correction. This correction is basically the failure of this Q preserving this splitting, which creates a Hamiltonian function. And we know, like, when you quantize Hamiltonian function, this one becomes a second order differential operator, and there's almost a unique one you can write down. That's the H bar BW operator. Okay, so if you go through all the details, you'll find this one. So this is standard quantization, basically the standard quantization of quadratic Hamiltonians. So I'm going to leave this the proof for you as an exercise. So, okay, so just let me say proof exercise. But this is actually a very important calculation if you haven't seen this before. It's a very quantum mechanical calculation. Now somehow we know what's happening. The meaning of the quantization, basically, I mean, in quantum mechanics, when you quantize some system, you got some kind of state space in the Fock space, whose classical limit is the Lagrangian submanifold. So if you want to write it down explicitly, this is what's happening. So let me just tell you. Definition. An element, let's call this one F, which has a genus expansion. This is basically every element here is a function on my V plus, some kind of invariance, and with a quantum parameter H bar. This one is set to satisfy quantum mass equation or quantum BW mass equation. Sometimes we're going to write QME. If basically the Q hat is a closed element in this space. So it's Q plus H bar partial P applied to this generating function equals 0.
What is Q hat square?
Square 0.
It's 0.
Yeah, this. Because Q and P are compatible. Yeah. And this is called a quantum mass equation. So I will tell you a bunch of explanations of this equation in a minute. But you see, like this is like a derivation. This is like second order operator. So like a second order differential equations. When you apply to something, you get like the two derivatives applied to the same object or applied to different object. So this is equivalently written as the Q plus H bar partial P applied to F plus 1/2 bracket F equals 0. That's a somehow more familiar structure. And from this expression, you can see, like, if you send H bar goes to 0, this equation, the leading term is already a classical mass equation. Like, the leading term is like QF0 plus 1/2 bracket F0 is 0. It's really a classical mass equation. So that's the quantum version of this equation. So now I want to keep this this blackboard.
Q is a Hamilton, is a quantum.
It's what I call BW operator in the previous lecture.
But you said it's quantization of the Hamilton.
Yeah, you remember like classical mass equation is written in such a form just now. This bracket give you the classical equation. Yeah. But this is a quantum equation. Okay, so let me say a few words about explanation. I mean, you see like literally this equation quantizes this one, but quantum mechanically this is has a very precise physical meaning. But what's really happening is the following. This is what usually physicists will say, like classically you have some kind of Lagrangian, that's the characteristic variety of some kind of D module, and you find some reputation and you find some states in the Fock space. That's precisely this process. So, for example, let us denote this state F, roughly speaking, by this object, phi, intuitively. And somehow, we would like to write this object as something like, if you think about this Fock space as generated by some vacuum state, it's like E, F, or H bar acted on the vacuum. Roughly speaking, that's what you're going to write in physical notations. And because functions here consist of like creation operators. And so what's really happening is the following, like we want this quantum mass equation which says that precisely this closed under this Q hat. So the quantum mass equation is the same thing as saying that this Q hat is induced from Q by this identification. So this equation is the same thing as saying that this state is closed under this Q action in the Fock space. That's a more intrinsic way of writing things. By the way, this equation doesn't depend on V minus. You only need V minus to write down the generating function. So it's like you only need to split into write down invariance. If you don't care invariance, that's where you should start with. Because it's only require like wire algebra is an annihilation operation. So that only depend on V plus. But you can implement this equation as some kind of generating function. So then you need the V minus to write down things like that. And you change V minus, you change the generating function, and that's related to the homomorphic normal equation. But anyway, this equation in physics is called a quantum gauge condition, the quantum gauge condition, consistency. It's like a Q is like a BRST operator, so which somehow generates the symmetry and then gauge symmetry. And you want to quantize get a state which is gauge invariant. So that's the quantum gauge invariance. Now, once you know this one, then you can pass to Q cohomology. And in physics, this Q cohomology is called really the physical states. So what's happening if you pass to the physical states? You find like this class of this state. Basically, it's an element of the cohomology of the Fock. Okay. Now, usually you see like this given by a bunch of tensors of something, and so it's computed by the cohomology on the annihilation, things like that. And usually, if you pass to cohomology, it becomes finite dimensional. Like even if you start infinite dimensional case. So then we're gonna write down the corresponding information on the cohomology in terms of generating function, like invariance, quantum invariance, how this works. Then this is the place where you need the splitting of the Hauge filtration. So let me just explain a little quickly. So suppose when we pass to cohomology, we write everything like, say, H is the one we wrote before, the same notation, like cohomology of the space, and the H plus. Did I use H or I think I use this notation. I forgot which one I used. I used a better one? Okay. Great. But we don't have the opposite one because this Q doesn't preserve this V minus. But anyway, so Q is compatible with omega, so this one is again symplectic. And this one is isotropic subspace. But at the cohomology level, we don't have the negative part. So what we're going to do, we choose one as a data. So we choose a polarization the negative part, the same thing as L. So this is like a isotropic splitting.
Actually, we want this to be Lagrangian splitting, but if it's infinite dimensional, then
Yeah, it's infinite dimensional, it's a little bit subtle. But if finite dimensional case, it's a Lagrangian splitting, yes. You're right. And then this splitting allows us to write down all the process we have just done at the cohomology level. So I'm gonna erase this part. Okay. So now remember, like previously, we have this relation like Y algebra and quotient to Fock space. Now you pass to Q cohomology because it's like given by tensors of the linear space and the linear differential. So you pass to cohomology, you really find like Y algebra of your H, and then map to the Fock space of the V plus. If you pass to, oh sorry, this H plus.
Vector space, like in general, the deformation quantization will map to the geometric quantization.
Don't have the from the deformation quantization. Formally, you don't have the map to geometric quantization. But unless you identify the H bar with a discrete value of the tensors, the Chern class basically. So you want to identify this deformation quantization with the geometric quantization. You have to do this identification. Right? H bar is 1 over K. You can do that asymptotically. You can do you can write down asymptotic you can use pseudo differential operator to write down some. Yeah. That's right. Yeah. Yes. Now, then we still want to write this one as somehow like a generating function. Then the choice of the splitting allows us to identify. So again, this choice allows us to write like H.
Because you have an element one in the unit vector in the Fock space, so you can get it.
Exactly. That's why it's annihilation. Yeah. Exactly. Yeah. Then you have to like functions on the H plus formal functions embedded here, which map to this one isomorphically. And now, because in the beginning, if you solve this quantum mass equation, so you have a state which is Q-closed, you relate to, you give a state here, basically, at the cohomology level. And then under this that identification, you obtain basically a formal function here. So it's going to be, you can rewrite this one as like, it depends on choice of a splitting now. So this process is not easy to calculate. That's why hopefully I can explain to you some calculation on the curve example. This is really not trivial. But anyway, so if you do this calculation, this element it's going to be the function. It's going to be functions on this H plus. That's going to be the quantum invariance.
Definition.
Yeah.
The calculation of what?
You want to compute this one by this process. It's highly.
It's just a definition.
Yeah.
And also, you are using the fact that the Fock space of the cohomology is the same as the cohomology of the Fock space.
Yeah, because Fock space is basically tensors of this creation of the same argument. But everything depends on the Hodge-Durham generation argument. But anyway, once you have that, then everything works fine. So finally, just let me say a few, two.
So again, in this language, what is a Hodge-Durham degeneration in this language?
You want everything, like the splitting works. The splitting, somehow you want, for example, you want, under the choice of splitting, you want the whole cohomology to be the cohomology of this. This identification. No, I mean, well, if you. Yeah, in general setting, no, nothing. Yeah, if you want to get the B model invariance, you want on Calabi-Yau. Yeah. This is always okay. Yeah. You want to get literally this B model invariance. Then you need to do something. But anyway, so this is roughly the process in the finite dimensional setting. So let me just say a few words about the B model and then the problem, and this will motivate us to basically invent some technique to do renormalization. I will explain this one next time. But basically, if you try to do everything on B model, the problem is about this even dimensional case. So it's like a Sx like polyvector field. And same thing for S plus and minus. And so you basically want to do something like quantum mass equation apply, want to define quantum mass equation. Literally, this is a yield defined. Because this P basically is P is singular basically. It's like distributions, and you put a bunch of distributions inside some integrals, and things like that, and you will basically run into trouble quickly. So that's the standard issue about so-called ultraviolet divergence in quantum field theory. And the next time I will try to explain like how to resolve this issue, how to really make a well-defined quantum mass equation. And basically the idea is like you have to regularize this one using this kind of elliptic operator. This is a place we're going to choose a Kähler metric. And then define all these diagrams, basically these pictures, in a homotopic way. So I will do this next time. Okay. So probably it's a good time to stop today.